And this expression is just to tell you that indeed there are field components that we normally don't see, but if you are very close to the aperture, then of course you start seeing it, and then you can use it for applications. Okay, let's get that. So let me spend some time on nanoscale confinement of matter. What really happens if you have electrons in nanoparticles? Okay. And as again Padmaja mentioned yesterday in our introductory talk, anytime you talk about nanoscale lengths, often you have to invoke quantum mechanics. Okay, that is the reason why this is also called quantum confined materials, because to understand the properties you have to use quantum mechanics. Okay? Of course, we will try to skip quantum mechanics, but still try to explain some phenomena in a very qualitative way. And so let's read this. So quantum confined materials, they refer to structures which are constrained to nanoscale lengths in 1, 2, or 3 dimensions. Okay? You can have a quantum well, a quantum wire, a quantum dot. And the length along which there is quantum confinement must be small compared to de Broglie wave. Okay, again, when I say something has to be, the length has to be small, okay, what does that mean? And it has to be small compared to something. So there is this characteristic length called de Broglie wavelength, okay? And it is the wavelength of electrons, and it's basically given by, we have said this before, electrons have a wavelength. So wavelength of electrons is given by this Planck's constant divided by momentum. And if you have electrons at thermal energies, then kinetic energy of electron, of course, is half mv squared. If it's a thermal energy, you probably have learned that it's of the order of kT. K is the Boltzmann constant, T is the absolute temperature. Okay, I mean, as temperature increases, electrons start moving more and more, right? As temperature decreases, electrons slow down. Okay? So that's the reason why kinetic energy of the electrons is proportional to the temperature. And from this, you can easily figure out, wavelength is h over mv. It turns out to be this. Okay. So if you want to know what should the size of a nanoparticle be, so that you start seeing quantum mechanical effects, then the answer is this: that it has to be of the order of this number or smaller than this. Okay. And so if you put in some numbers here, let's say for 10 degrees Kelvin, very low temperatures, you can calculate the Broglie wavelength in gallium arsenide. It's about 162 nanometers for electrons. And let's not worry about volts. So what it tells us that if you want to have nanoscale quantum effects, then the size of the structure has to be less than 162. Okay. And of course, if you raise the temperature, if you bring this to room temperature, 300 degrees Kelvin, then of course, the size of the structure has to be still smaller. So obviously, if you want to see nanoscale effects, the size has to be 5 nanometers, 10 nanometers, 15 nanometers. Only then you will see quantum mechanical effects. Okay, so let's see. Yeah, okay, here, maybe I'll come back to this. So the question is, how do we design quantum confined materials? Okay, it is okay to talk in theory that if I have very small particles, then of course these will be the quantum mechanical effects. But the question is, can we design something which can be used for real applications? And here is a very nice example which I want to maybe just spend some time on. So here I want to talk about what is called nanoscale confinement in one dimension. Okay? And so this nanoscale confinement in one dimension is also called a quantum well, because it is just the well is only in one direction. Okay? The electrons are confined only in, say, z direction, not an xy direction. Okay? And you can build this quantum well in a very easy way, and let's see how this is done. So what people do is, they take alternating slices of different semiconducting materials. So here, for example, I have gallium arsenide surrounded by aluminum gallium arsenide. Okay? And the question is, what is the difference between gallium arsenide and aluminum gallium arsenide? The big difference is that the band gap in gallium arsenide is smaller than the band gap in aluminum gallium arsenide. Okay? And here, of course, I've given some numbers, and I'll explain what that means. The band gap of gallium arsenide is 1.43 eV of aluminum gallium arsenide is 1.79. So this band gap is more than this band gap. Okay? And let's go back to the earlier slide, what that means. Okay? So what this means is, for gallium arsenide, the band gap is smaller, but for aluminum gallium arsenide on either side, the band gap is higher. Okay? What that means is, suppose I have excited electrons to this conduction band in gallium arsenide. Remember what I had said before, that if you want free electrons, they must be in the conduction band. Okay? So suppose there are electrons in conduction band in gallium arsenide. Okay? They are free to move here. But on either side, you have aluminum gallium arsenide. Okay? So these electrons don't have enough energy to go into the conduction band of aluminum gallium arsenide. Okay? So they're just trapped here. Okay? So you can see that it's like a web. If you just have a slice of gallium arsenide surrounded by aluminum gallium arsenide, if the electrons don't have enough energy, they'll be trapped in this. That's the reason why it's called potential. Okay? And so it looks like this. You have gallium arsenide, this is an energy diagram, gallium arsenide, aluminum gallium arsenide. The electrons are here in the conduction band, but they don't have enough kinetic energy, so they are trapped inside this web. Okay. Now, what does this mean? Just recall what I said way back in the beginning, that so you have these electrons, bouncing back and forth between the walls of this quantum web, and these electrons can also be thought of as a wave. Now, this problem you can easily analyze in quantum mechanics in a particle in a box, okay? And then find out what are the allowed energy of these electrons. But an easy way of thinking about it is that electron is like a wave. Okay, so you have a wave formed inside it, and of course the wavelength of this wave is constrained by the dimensions of this well. So if the well is wider, then the wavelength is longer. Okay? If the well is narrower, the wavelength is shorter. And how does the length, the wavelength, how is the wavelength related to energy? Does anyone know? If the wavelength decreases, what happens to the energy?
Increases.
Increases, exactly. Like wavelength of blue light is shorter than the wavelength of red light, right? So energy of a blue photon is more than the energy of red photon, isn't it? And so you can see that the energy of these electrons, just by changing the size of this quantum web, I can change the energy of the electron. And that is the reason why we have these semiconducting nanoparticles. If you make a nanoparticle smaller, it emits blue light, okay? Because the energy levels are higher. And actually, this can be worked out very nicely in quantum mechanics. And whenever you take this undergraduate course in quantum mechanics, you can easily work it out. And it turns out that the energy is just inversely proportional to the square of the length. Okay, so if you make the length smaller, the energy becomes higher. It's a very qualitative picture of why different sizes of nanoparticles they glow with different colors. And this is, maybe I can just show a little bit more. So,
Dr. Sharma,
yeah, go ahead.
in your previous picture,
Yeah.
slide,
Yeah.
how important is the thickness of the aluminum gallium arsenide as
Yeah.
far as the keeping the particles from leaking out?
Yeah, I mean, that's a very good question. So, of course, here, for example, we want that these electrons remain. I mean, if you look at the wave function, there will be a tail here, okay?
Yeah.
And obviously, you don't want the length of the tail longer than the width of this aluminum gallium arsenide. So this has to be sufficiently thick compared to the length of that tail of the wave function. But actually, there are other types of structures that I did not talk about. They're called multiple quantum wells. So here, you actually want these neighboring quantum wells. This is one quantum well, this is another quantum well. So you want these quantum wells to actually interact with each other. Okay? And in that case, obviously, you want this light to be thinner because you want this tail to penetrate it. Okay? So you have new types of quantum wells which I can talk about. Anyway, so this is what I was telling you. This is the wave function of electron in the lowest state, and you can see that it has a very long wavelength. But with higher energy, the wavelength is becoming much shorter. If you go to still higher energy, the wavelength is becoming even shorter. Okay, so this wavelength and energy are really inversely proportional. Okay? And so these are the energy levels in the conduction band, and you can actually tailor these energy levels to anything you want. Okay? And whenever these electrons fall back from conduction band to valence band, they emit light. Okay? Now, because you have tailored these energy levels, so of course, you can essentially, I can move this energy level anywhere I want just by changing the thickness of that slice. Okay? So what that means is that I can get any wavelength out from this quantum well just by changing the thickness. Okay? And that, of course, is very, very important, for making new types of lasers. If I want to make a laser with precisely 400.629 nanometers, I can do it by this nanoscale engineering. Okay? So, and in fact, this is done. You can buy quantum well lasers in the market. So this is what I was telling you. So just by changing the size, actually, you can change the color. Actually, it's much more than that. I mean, these lasers are actually very, very strong. Because why? Because earlier in an ordinary semiconductor, in a bulk semiconductor, the electrons can have all these energies. Okay? But because of quantum mechanics, because of quantization, now only few energies are allowed. Okay? And so you have lots of, just because the electron can be either here or here, that means the density of electrons is very high. Okay? Electron cannot be anywhere here in between. They can only be here or here. And so the density of electrons is very high. So what that means is that when you get this emission, this intensity of light is very, very strong. Okay, so you can make very strong lasers in a very efficient way. And you can have new transitions and so on. And so there are all sorts of quantum wells. Here actually what I'm showing is you can have quantum wells in all sorts of semiconducting materials. And just by changing the size, you can change the wavelength. And you can have other types of quantum wells as well. You can have a low band gap material surrounded by a high band gap material. So there are all sorts of possibilities. And I won't get into that. And okay, so I don't know how much time we have. I'll just take maybe 10 minutes more. So, coming from semiconductors to now metals. Okay. Obviously, we have only talked about semiconducting particles, quantum dots. Now, metals are different from semiconductors, right? I mean, in a semiconductor, if you want to have free electrons, you must excite them from valence band into the conduction band. But metals are different. To begin with, you have lots of free electrons. Okay. So, let's say I have a nanoparticle, and if I shine a laser on that nanoparticle, there are so many free electrons, and they will start oscillating at the frequency of light. Okay, and if certain conditions are right, then you can have very efficient transfer of energy from light into electrons. Okay, so you can have what is called resonance. Okay, I mean we know resonance in sound wave, for example. I mean, if you have cavities of the right shape in certain